Hi, in this example, we are going to see how to design a logic function using a multiplexer. Actually, multiplexers are generic devices in that they are able, we are able to design any logic function using only multiplexers. Okay, maybe just only one multiplexer, like in this simple example, or combining various multiplexers, as we will see in examples later. So, in this sense, multiplexers are one of the most useful devices in combinational circuit design. Okay, so there are different techniques, and design using multiplexers is actually based on the Shannon's expansion theorem, okay, that we have seen in the slides. The Shannon theorem may look a bit scary, actually, but it's very simple. So I will try to show you how we are actually using that theorem when analyzing a function and splitting the function so that we can implement it using a multiplexer. Okay, so in this case, we plan to implement this function with 8 to 1 multiplexer, means 8 data inputs, so we have 3 selection inputs. I will start by drawing this multiplexer. You see that in the unit we used to use that symbol for the multiplexer with a corner here. Okay, this is a symbol you can find in old books, but maybe it's a bit old-fashioned. Okay, we use that old-fashioned symbol in these slides. Multiplexers can be represented in different ways, actually. Sometimes simply as a square block, as I will do in this example. So so that you see that different options are possible when describing circuits. So this is our multiplexer. We have 8 data inputs, 1, 2, 3, 4, 5, 6, 7, 8. And we have 3 selection inputs, 1, 2, 3, and this is the output of the multiplexer. Okay, so first thing is I will mark this one. This is MUX 8 to 1. Okay, because we are drawing simply a box, square box, we need to put a name or something to indicate what device it is, because the shape doesn't inform about the device. Now I number the inputs. I number the selection inputs to 1, 0. It's very important to put the numbers so I know what are the most and the least significant inputs. Okay, and the data inputs. 0, 3, 4, 5, 6, and 7. When we design a function with one multiplexer, like in this case, we want the output of the multiplexer to implement my function. Okay, so I have to find out what do I have to put in the selection inputs and what do I have to put in the primary data inputs. Okay, so because my function depends on variables x, y, and z, the idea is that we will use some or all the variables in the selection inputs, and when we will use the data inputs to put here the adequate values so that the multiplexer generates the correct value for my function. Okay, this is the basic idea. Like in this case, I can actually use all my variables in the selection inputs. Okay, so we will do it like that. We will use x here, y here, and z here. And now in this condition, depending on the value of the variables, we will select one input or the other. It's now to make the multiplexer behave like my function. I will have to program or to set the data input to the appropriate value. It can be, the appropriate value can be seen in different ways. Okay, I will use a kernel map in this case, so I will represent my function in a kernel map. A truth table is also possible. There are many possibilities, but because we are already used to represent things with the kernel map, I will use that. So this is the kernel map for my function. And so this is f. I use more, yes, I use more than really needed here. Okay, so I don't really need all that because it's only 3 variables. 1, 2, 1, 2, and 3. So you see that it's very realistic. I'm not copying the problem. I'm just solving it again. Okay. I don't really remember how long it is. I solved that problem last time. So I need that map here. Move my function here. Inputs are x, y, and z. 0, 0, 1, 1, 1, and 0, 0, 1. I put the information in my kernel map. So these are the minterms 2, 3, 6, and 7. Because the way I have sorted, I have ordered the variables here. This is minterm 0, 1, minterm 2, 3, 4, 5, 6, and 7. Okay, that's my function. We don't want to simplify, we don't need prime implicants. It's for designing with logic gates, for minimization. Now we have a different story. We have a multiplexer, okay? So what I will try to find in the map is the values that I have to put in the primary inputs here, okay? So let's go through the multiplexer. What happens when variables are 0, 0, 0? When variables are 0, 0, 0, what's the section of the map that corresponds to that value, to value 0, 0, 0? This is just this place in the map here, okay? Maybe green is not the right color here. I'll use this purple, something, okay? So this is the section of the map, okay? The subset of the map that corresponds to x, y, z, 0, 0, 0. I draw a square because I'm not doing minterm, something like that, okay, to differentiate. But it means that when inputs are 0, 0, 0, the function that remains here is a function which is only this square and should be 0. I mean, I have only put the ones, but the rest are zeros. So I know that basically it means, using Shannon's expansion theorem, that f, when variables are 0, 0, 0, becomes another function, but this function is very simple. It's a function that is equal to 0, okay? So now the idea, I want the multiplexer to make my function. So in this case, 0, 0, 0, when I put this value in the selection variables, the output of the multiplexer will be whatever I put here, where I put in this input, data input here. If I want the value of my function to be 0, I just have to put a 0 here, okay? So I take I analyze the the subsection of the map that remains when I use that particular value of the variables, and this value I put it here, so that when I use those variables in the selection, this is the value that goes to the output. Okay, I want you to see is that this small piece of the map correspond to this input in the multiplexer, because the way we have connected the selection variables here. So I just repeat, when inputs are 0, 0, 1, I want my function to be 0. But when inputs are 0, 0, 1, I'm selecting input 1. My function will be equal to whatever I put here. Because I want it to be a 0, I put a 0 here. So it's just copying the sections, which in this case are the minterms, to the multiplexer. When inputs are 0, 1, 0, I want a 1. 0, 1, 0 means selecting input 2, so I put a 1 here. Input 0, 0, 1, 1, I want a 1 in my function. 0, 1, 1 will select input 3. Because I want a 1 in my function, I put a 1 here. For input 4, I want a 0. For 5, I want a 0. For 6, I want a 0. And for 7, I want a 0. Oh, sorry. I want a 1 here and a 1 here. So that's it. This multiplexer will make my function. It's 0 whenever the function is 0, 1 whenever the function is 1. Okay. You see, this set of values is just the truth table of my function. Okay, just because I have selected these variables. Great, isn't it? So actually, this multiplexer can make this function of 3 variables, but could make any function of 3 variables. If we have a function with different set of outputs, we just connect them here, and then we can reprogram the multiplexer to give a different result. In that sense, it's a universal device. If you remember from the previous unit when we talked about FPGAs and how FPGAs had those configurable logic blocks, that I can make configurable logic blocks to behave like any logic function, like an AND gate or an OR gate. Actually, what do you think? What do you think they use in FPGAs to make those blocks very configurable? What they use are what are called lookup tables. Okay. And a lookup table is basically a multiplexer connected to a device that can store bits. It's a piece of memory. Okay. So that way that's why you can reprogram or reconfigure an FPGA. Okay. When you have some logic function to do, what you do is that you load that small memory with the values you want in your function, and you put the inputs of your function in the selection inputs. More or less, okay? The lookup tables in the FPGAs are a bit more complex, but that's the basic idea. If I make those inputs configurable, I mean, if I can delete that data and load new data here, then I have a device that can be reconfigured to implement different functions. Okay, so that's why multiplexers are so important. With only multiplexers, we can implement any function, and we can change the function very easily. That's why they are the basics for lookup tables in configurable devices. Okay, so that's all. Thank you.